Okay, so on this one, I'm going to do the solution for this composites handout problem that I talked about in class on Tuesday. So I'm going to solve it in Mathematica. I already kind of did this. You can do this by hand as well. It goes the same way, but I'm a big proponent of using Mathematica. I think it makes your life a lot easier, and I think it actually makes you able to solve much more complicated problems than you could by hand. So this hopefully will help demonstrate it a little bit. All right. So the first part, so basically with this problem, you're given a composite material with a certain volume fraction and certain material problems for the carbon fiber and the epoxy, the matrix. So we consider, to get the effective properties for this composite material, we look at a very small representative volume element, if you will. So here we pick one that happens to be 1 micron on an edge, so it's a cube. And then we apply a force on it of 1 Newton, okay? And we're going to go through and find how much force is in the fiber, how much force is in the epoxy, and then from that we can determine, well, the stress and the strain we can determine because we can get the elongation. And then once we have that, we can figure out what's the stress in the fiber and what's the stress in the epoxy, determine at what point they will fail, and then from then kind of talk about the effective strength of it. Okay, so I first did this problem with the 1 Newton force. That was a little high. You get the same answers with 1 Newton or a smaller force, but when you use the 1 Newton force, you get very large stresses and very large strains. They're not really realistic, but since we're doing everything linearly, it's fine. I'm going to change a little bit. I'm going to use 5 times 10 to the 3rd newtons as the force, okay? And you'll see why in a second, but it goes the same way. All right, so the first thing we do, other than having a nice header here in Mathematica, is we define the problem parameters and the material properties. So we're going to write everything in terms of meters, pascals, and the densities we'll keep in grams per centimeter cubed. Right? There's actually a units function that'll keep track of units for you in Mathematica. I really don't like it. I don't think it works that well for engineering problems, so I'm not going to use it. I'll just keep everything in meters, pascals. So we get the exponents here. So here's the Young's modulus for the fiber and the epoxy. Here's the maximum stress for the fiber and the epoxy, and here's the density for the fiber and the epoxy. That's just from the table given. We scroll down here, and then we define the length of an edge, the volume fraction, and then the load applied. So here's the one that I knocked down to 5 times 10 to the minus 3rd. Okay. All right. So those are the problem parameters. Now for the first problem, well, I should probably evaluate them, right? So I need to evaluate them. So we do Shift-Enter to evaluate those. There's the first input. Shift-Enter to evaluate those. I have the semicolons at the end, so it doesn't spit out the answers. If you remove the semicolons, you'll see the answers, but you know it's evaluated because you've got this line 1, line 7 thing. All right, so the first thing we need to do is solve for the forces in the fiber and the force in the epoxy. So I'm going to call P fiber the force in the fiber and P epoxy the force in the epoxy. And again, the way we have to do this is using sum of forces in the y direction and also the fact that the elongation in the fiber has to equal the elongation in the epoxy. So those are the 2 equations, and that'll allow us to solve for the 2 unknowns, the load in the fiber, the load in the epoxy. All right. So first I write the force balance equation. It's relatively easy. So this here is actually the force balance equation. I'm going to give it a name, some force. Okay, so this is a little tag that just refers to this equation. But the equation is actually the load in the fiber plus the load in the epoxy has to sum to the total load applied. All right. Okay. I have the double equal sign to show that it is actually an equality that has to be enforced. This whole equation I'm going to call some force. So that's why there's this single equality here. So some force equals this equation. All right? That's just sum of forces in the y. We define the cross-sectional area as the length squared. Well, let me evaluate this first. And so here you can see, here's the equation evaluated. The force in the epoxy plus the force in the fiber has to equal the P force, and it substitutes in the 5 times 10 to the minus 3. Now let's get the cross-sectional area. That's the length cubed, the squared, excuse me. The area of the fiber is just the volume fraction times that area, and then the area that's the epoxy is 1 minus the volume fraction times that area. Shift Enter. These are the actual values. They sum to the total area. So here's the total cross-sectional area. Here's the cross-sectional area that's fiber, and here's the cross-sectional area that's epoxy. All right. We need to define this compatibility equation, which I've written down here. And the compatibility equation for this one is that the elongation of the fiber has to equal the elongation of the epoxy. So here, I've defined the elongation of the fiber and the elongation of the epoxy in terms of the load of the fiber and, the PL over AE equation. All right? And so here it simplifies it. So here it tells you that the elongation of the fiber is this, 0.00117509 times the load of the fiber, and the elongation of the epoxy is this, 0.00063 times the load of the epoxy. All right. So now we can write the compatibility equation. Again, the compatibility equation is actually that the elongation of the fiber has to equal the elongation of the epoxy. We're going to set these two together, and we'll call that compatibility. And there it is, right? So this is the equation. Okay? So now we have two equations here, this one and this one. Two unknowns, P epoxy and P fiber. So we need to solve them, okay? In Mathematica, you can do this by hand if you want, but again, Mathematica has this solve function. Here it's solving these two equations for these two unknowns. And it's giving a name to the solution, it's just calling it solve. So that's the way it works. So here's the solution. You can see this is solved, and it says the load in the fiber should be 0.0049, and then the load in the epoxy should be this 0.0000, whatever, 908,566. And those values are stored in the solution. So that's the answer to problem 1. So now we've solved it. We know the load in the fiber and the load in the epoxy. Now if you use the 1 Newton, your answer will just be, scaled linearly. So you're using 1 Newton, that means that actually everything is going to get multiplied by 1 over this value. Okay? And I forget what that is, but it's a big number. So these values jump up very high. These are a little more reasonable. Okay. All right, so the second problem is determine the effective Young's modulus. So every time we talk about effective, as we mentioned in class, this is referring to the Young's modulus of this system, this composite system consisting of the fiber and the epoxy. Okay. So if I consider it to be a homogeneous material, that's what you would get, right? So to do that, we're going to use this relationship that it's this effective stress over the effective strain. So we need to define both of those, all right? Okay, so we need to get the effective stress, which is just the P over the total area. So this is the total load applied over the total area. That would be the stress if it were uniform material, right? And we have to divide that by the strain effective. And the strain effective is easy. That's just the elongation, okay, divided by the original length. So the elongation is the same for the fiber and for the epoxy. They're equal. And so I'm just defining delta as the elongation. Here I'm saying it equal to the fiber. You could do to the delta epoxy, you get the same answer. I have to do this little trick here, this little bizarre Mathematica notation means take the results in the solution, this solution from the solve, put it into this variable. Okay? So it just puts the number 0.0049, well, which one? Puts in this value for P fiber into this equation. You see here, actually, delta fiber is defined as this in mathematics. I need to substitute in the numerical value for P fiber from this solution. So that's all this is allowing me to do. If you didn't do that, then I would just get that delta equals actually this, right? And then here's just saying the strain effective is the change in length over the original length. So here you go. So here's the elongation, and here's the strain, all right? Now we can get the effective stress. That's just the force over the area. And now we can divide the two and get the effective Young's modulus. And so here it is. The effective Young's modulus is 86 gigapascals, okay? And that's it. So what this Young's modulus is now we can treat this material, if you will, as a homogeneous material. Its stiffness is this 89 gigapascals. So now you can just say, well, it's one material, and that's the Young's modulus. If I change the volume fraction, obviously I have to go through this calculation again. All right, the final problem wants you to determine the strength, okay? And there's two ways to consider the strength. The first type of definition is, well, obviously, the fiber and the epoxy will fail at different loads. Typically what will happen is you'll pull, the epoxy will start to fail, and then the fiber will fail. Now, do you want to define failure as the fiber failing? That would be the less conservative, or as the epoxy first starting to fail. That would be the more conservative. Usually it's actually somewhere in between. We're going to take this kind of extreme one that as soon as the epoxy starts to fail, we're going to call that failure. So this is a very conservative definition of failure for a composite. So to do that, we need to compute the stresses in the fiber and the epoxy and compare those to the maximum stresses allowable in the fiber and the epoxy. So basically what I'm doing here is I'm going to compute a factor of safety in the fiber and a factor of safety in the epoxy for this 5 times 10 to the third Newton force. So here we have the stress in the fiber is the load in the fiber divided by the area of the fiber, and the stress in the epoxy is the load in the epoxy divided by the area of the epoxy. And here you go. So these are the answers. So we have 13 gigapascals of stress in the fiber and 144 megapascals of stress in the epoxy. So now we get the factor of safety. We're just going to take the max stress allowable and divide it by the stresses that we have. They're all less than 1. So that means that they all fail. We get failure in the epoxy. Oops, here, failure in the epoxy and failure in the fiber. But what you can see here is actually the failure in the fiber will, the failure in the epoxy will happen sooner. It has a lower factor of safety, even though the stress in it is lower than the epoxy, lower than the stress in the fiber, but it has to do with the ratio, right? So failure will happen first in this one. So we have to figure out what is the maximum load at which, you basically get we want to have a factor of safety of 1 or higher for both of these. So since it's a linear problem, if you have the load, then you've doubled the factor of safety, okay? In other words, if you half the load, the stresses drop in half, so the factor of safety doubles. So all we're doing here is we're just scaling the actual force by whichever factor of safety is less. And then likewise here, we'll get the max stress as this maximum force applied over the cross-sectional area. Okay? And so here you can see the maximum stress allowed is this 200 megapascals. Okay, so that becomes the strength of the epoxy. Okay, down here I do some other ones. I get the density, and we also get the sort of strength-to-weight ratio, and then I also look at what happens if we consider the other definition where failure is, that the fiber fails. And you can see that obviously goes higher. That gives me to 1.7 gigapascals.
Okay.